So here was the question I asked at the end of the last part of the lecture, where we were thinking about what the energy bar chart would look like if the axes were on the ground. So remember that the gravitational potential energy is mgy. And in this case, we are now saying that the final value of y is 0, because we've defined y equals 0 on the ground. And so C and D cannot be correct. Also, C can't be correct because at the initial time, the ball is at some non-zero value of y, a positive value of y, and so the initial gravitational potential energy can't be 0. So the answer here is B. Now, an important point. This means our energy bar chart is different, and so our conservation of energy equation will be different. However, we have to come up with the same answer that we did with the other choice of axes. After all, this all has to be consistent with experiment, and if we did this experiment, we would definitely come up with a particular value of the final speed of the ball, and it doesn't matter where we define our axes. The situation where energy is going to turn out to be really important is when we have forces that depend on position. So let's now take a look at one of the simplest examples of that. Way back, we saw spring forces, and we've hardly talked about them at all since then, so let's get a bit of a review. A spring force always acts back towards the equilibrium, and what I mean is that any spring has an equilibrium length, the length that it has when no forces are being exerted on it. But if you pull on a spring so that it stretches, so the displacement of the end of the spring points in some direction, then the spring pulls back on your hand. That's what we call the spring force, the force that the spring exerts on you, and that spring force points back towards the equilibrium position. And similarly, if you push on the spring so that your displacement is like so, then the spring force again pushes back towards the equilibrium position. We call this a restoring force. In other words, the spring force is always in the opposite direction to the displacement vector for the end of the spring. The other thing we know about spring forces is that when you pull on a spring, then it pulls back. And if you pull it so that it stretches longer, in other words, if you increase the displacement of the end of the spring, it pulls back with a larger force. So the amount of force, the magnitude of the spring force, depends on the magnitude of the displacement of the end of the spring. And similarly, if you compress it, you get the same thing. The amount you compress it affects how large the spring force is. And so we say that the spring force is proportional to the displacement, and there's this constant, which is a property of the individual spring, which gets called the spring constant. I don't like the name spring constant. I don't think it's descriptive enough. I think it would be better if we call it the stiffness of the spring, because that's really what it describes. Or if you write it as a vector relation, now you have to include the fact that the spring force points in the opposite direction to the displacement vector for the end of the spring, and so you need this negative sign out here, which is just saying that these two vectors are in opposite directions. All the methods we know of at the moment deal with constant forces, but here the spring force we see isn't constant. It changes with the length of the spring. So as we're going to see next lecture, this is the sort of situation where energy really comes in handy. Now that we've spent some time on kinetic energy and gravitational potential energy, it's time to generalize our idea of energy somewhat so that we can move on to other forms of energy. So, remember that energy is all about change, and so we need some language to talk about change. The state of an object or system is the set of all measurable quantities that can describe it, and this will be useful for talking about changes. So, all changes of energy are associated with changes of state. And notice something, energy is abstract. You can't see it, you can't even directly measure it. But changes in energy are always associated with changes in more concrete things that you can see or measure. So, thinking about our ball, we see we've had changes in speed, and those are associated with changes in kinetic energy. And we have changes in height, which are associated with changes in gravitational potential energy. Now, notice something about that change in height. That's actually a relationship between two objects. It's effectively the distance between the ball and the Earth. And so the gravitational potential energy is only part of the system's energy if we include both the ball and the Earth in our system, which is a subtle but important point. If we don't include the Earth, we're not saying that there isn't gravitational potential energy. What we're saying is that the gravitational potential energy isn't in the system, it's part of the environment's energy. There's something else going on here, though, that's more subtle. There's a change in horizontal position, but that doesn't seem to be associated with any energy change. Why is that? So let's contrast the change in height with the change in horizontal position. The difference here is that there is a weight force acting on the ball which acts vertically, but there are no horizontal forces, and this shows us a bit of a rule which we'll elaborate on more later when we talk about work. Position changes only matter for energy purposes if there is a force that has a component parallel to the motion. Another state change associated with an energy change that we have seen is with springs. Reversible changes in length or shape are associated with spring potential energy. Notice this word reversible. If you have a situation like this car, where it has clearly gone through an irreversible change in its shape, that is not associated with spring potential energy. That would be associated with another form of energy that we'll talk about more later, thermal energy.